We've done our recap, so I won't repeat that. We talked about some of these things last time. We talked about how experimentally to determine these capillary pressure versus saturation curves. So really our object today is to try and think about a little bit about the controls on how deep the material can travel. And so it's a pretty straightforward analysis, and it just relies on us thinking about the exact form of these curves. So these are the curves we have already. This is the bubbling pressure. We know that it's hysteretic in that we increase pressures, we'll go up this saturation curve, increasing the saturation of the non-wetting fluid at the expense of the wetting fluid. And then as we reverse, we'll come down to this point. So I guess the important thing to realize is that for any given value of, actually we do it either way, right? Perhaps it's easier to think of it. For any given value of pressure, we potentially have two saturations, and we don't know necessarily how to choose between those unless we know the predefined wetting conditions of the system. And so what we can do is we can use this curve with this entry pressure to think about the transport of fluid vertically within the porous medium. And the analysis is pretty straightforward. If you think of a salad dressing, oil over water, you could think of water having supernatant oil on top of it. It has to be, in this case, denser than the water. So there's no reason why we couldn't arrange them stacked like this, because all that we're satisfying is that the forces that are applied across the boundary of these two fluids have to be in equilibrium with each other. It has to be the same force pushing upwards as is pushing downwards, so that we satisfy Newton's law. So it's not accelerating, and therefore the sum of forces has to equal 0. So that's merely that statement. So if we take that system and we pull down this upper surface so that it's depressed, then we can look at the force balance that occurs across this boundary. And the force is going to be equal to the pressure that's acting in the blue fluid, and that's going to be the height of the fluid multiplied by its unit weight. And so the depth of it is going to be the depth h plus some small amount that we pull it down, which we'll call delta h. And that's going to be the force that's acting, the pressure that's acting downwards. If we want to create it into a force, we can just multiply a pressure times an area. The area would be the horizontal area on this plane. And we can check to see if the force acting upwards in the water, or the pressure in the water acting upwards, is the same as, less than or equal to, the force acting downwards. And so the force acting here, from what we know, if we move horizontally, we know that the pressure acting at this point will be equal to this height of fluid plus this depth of water. And so the amount of force acting at this point is going to be the unit weight of the non-wetting fluid down to this point, plus the unit weight of the wetting fluid underneath this. So the sum of these two occurring here. And so by definition, the magnitude of the force acting downwards, which is acting through this depth, multiplied by the weight of the heavier fluid, rather than the weight of the lighter fluid, has to be larger. And so the reason that you can't typically have a dense fluid overlying a lighter fluid is that if you get this excursion from an exact planar feature, is the pressure imbalance will cause this lobe to become progressively deeper and deeper. And so it's unstable in the system. I guess it's like trying to put a ball bearing on top of a valley. It always wants to roll down into the bottom of the valley to find its equilibrium circumstance. So what we can do is we can use our idea of this entry pressure. I guess we can think of this entry pressure as being equal to a critical height of fluid multiplied by a unit weight of the non-wetting fluid. Talked about that before. It's just by definition what that is. And we can look at what would happen if we have that acting on the surface of a porous medium where we have the water table at the surface. And so we have a given height of the fluid acting here, And so if this height is equal to what we've called HC0, in other words, this bubbling pressure here, then we'd expect that this would be enough force for this to invade into the porous medium and keep on traveling until we deplete this. And once this is depleted, then there's nothing more to drive the flow. So what do we expect to happen? Will the plume stay there, or will it keep on going and detach from the top? Well, we can do the same example as we did before. We can look at the pressures across this boundary. And so the pressure acting on the upper part is going to be equal to the pressure acting downwards plus the entry pressure that it has to overcome. So this pressure that's acting is greater than this pressure plus PC0, which is what this is. Then there's no reason that this interface here can't keep on going. And so if we write this expression in terms of this equation, we'd write it in terms of either the heights of fluid. And the height of fluid that causes this pressure is going to be this height off to the side, the total vertical height of this. And if we substitute for these into this expression here, substitute this, P NW is equal to H gamma NW, etc., then we can rearrange it and we come up with a minimum value of this height, which is a function of the ratio of the unit weights of the two fluids. The non-wetting fluid has to be larger than the unit weight of the water, by definition, if it's sinking through it. And also a function of the aquifer, which is this entry pressure, which is just the, it would be just this PC0 over unit weight of the non-wetting fluid, by definition. And so that suggests that as long as this height of this ganglion is larger than H min, there's no reason that it can't detach itself from the surface and just travel down by translation. And the only way that it would stop is that if for some reason it went through a pore throat and it necked down so that it broke into two parts. And if the two parts that it broke into were both smaller than this minimum value, then it would just stop there and be held by interfacial forces and not travel anywhere else. So we can use something about the knowledge of the material properties, this bubbling pressure, and also about the unit weight of the fluids to be able to say something about the nature of travel within the porous medium. So there's no reason it has to be connected all the way to the surface. It just has to be that the pressure applied at the bottom of this, which would just be the same as the height of water in a swimming pool acting down here. It happens to flow be a continuous pathway through a porous medium, but it's no different than if it was sitting in a swimming pool, that this pressure is large enough to overcome the entry pressure and then keep on going, and in which case this will retract from the surface. It will retract, but the potential is that in retracting, from what we know about the behaviors that we'd expect to see, is that we'd expect to leave this, this chimney. And this chimney is residual material, which is just a smear that's left as it comes down. And we know that this probably can exist because we know that as we, that we're always left with some irreducible saturation of the non-wetting fluid, this amount that we have here, which is always going to be of the order of 10%. So this is in the saturated groundwater region. It would be 90% saturated with water, but the other 10% would be the residual product, which is present within the pore throats. So that's one way to be able to characterize exactly what behavior we would expect. The contradiction, maybe, in what we've talked about is that when we talked about this going into the porous medium from sitting on the surface, we said that the only resistance to this would be equal to the entry pressure, which this has to overcome, and therefore this would move as long as the height of the fluid was greater than this bubbling pressure to move into it. And then when we dealt with this, we have a different relationship, which says that the bubbling pressure has to be overcome by some different amount, because this expression is not equal to just HC divided by 1. It has this extra term included in it, which is the ratio of the units' weights. And so the reason for this difference is, if you think about what these two different geometries would be, this is the first geometry we looked at, where the entry pressure is just equal to the bubbling pressure divided by the unit weight of the fluid. And so that is if the water table is at the surface, and this is a 55-gallon drum sitting on top of the surface, then this would control the height of fluid that would cause invasion. This amount would be if the water table was not on the surface, but was at the level of the top of this. And of course, the reason for this, it could be here or it could be higher than this. The main point is that it's at least at the height of the surface here. And so what this represents is that the motive force of this that's acting downwards is just the buoyant weight of this NAPL that's sitting in otherwise a bath of water which surrounds it. So the full weight of this acting here is not acting, because it's only the buoyant weight of this column of fluid that's acting, because we have water all around it. If the height of the water column increases, it doesn't matter. It's still the buoyant height of it. I guess if the height of the water column was less than this amount, then not more than the full buoyant weight would be acting at this particular point. So I guess we have to be mindful of those two components. So that's what we need to look at. So that's all we have to talk about in terms of that today. We talked last time about the methods of being able to measure the magnitudes of these capillary pressures. We know what the ordinates of these are. We know that they're hysteretic, and we have scanning curves within there, so I'm not sure that we need to discuss that again. And I think that's all we really had to talk about today. So maybe just for a few minutes to go back to the last thing we talked about last time in describing what these are, just to perhaps repeat this, because it's really the essence of what we're attempting to understand. So we define things only in terms of two individual fluids. The fluids that we're dealing with are classified as wetting fluids, typically water for us, and non-wetting fluids, which are typically either these solvents, denser than water if it's below the water table, or in the vadose zone, we're interested in air, would be another non-wetting fluid, which plays counterpoint to the water. If we are dealing with these, we can use the same terminology in both. It's just that we're swapping the fluids. So in one case, we're looking at a NAPL in this case, and in the other case, we're looking at the vadose zone, which is this. And that we can look at these behaviors that we've talked about, and that is that with the groundwater surface here and the water table defined here, we can always, as a function of that water table, by definition, the water table is at atmospheric pressure, that's by definition. So as we go down from the water table in water, the pressure increases as the weight of water above us, so-called, the swimming pool equation. As we go down through a connected ganglion of NAPL, the pressure in that NAPL would increase according to the unit weight of that fluid. The difference between those, which are represented in the capillary pressure, define the capillary pressure between those. So it's just the difference between here that defines this. And so we can scale the depth, if you like, of this capillary pressure versus saturation curve in terms of this capillary pressure, which is, we can overprint as a particular depth on the porous medium. And so what we'd find is that the bubbling pressure, so long as we had a height of fluid that was enough to invade this, which is just our HC0, if that HC0 occurs, then it's able to get down to this magnitude here at 100 to overcome the saturation of the water. Below this, the saturation of the NAPL would be progressively larger and larger. And so as we increase the capillary pressure at greater depths, then the saturation of the non-wetting fluid becomes large. The saturation of the water, which has to be pushed out, becomes relatively small. And therefore, if you think about it, it echoes, or not echoes, I guess that's in here. It mimics the behavior that we see here, in that that's exactly what we see here. So this is at reasonably low saturations of the non-wetting fluid. As you come down into this material, it would be 80% saturation of the wetting material and 10% saturation of the water, just as we saw in the base of our diagram, which is replicated on here. So along this bottom part here, this part here is a small, it's upside down, right? So a decreasing saturation of the wetting part and an increased saturation of the non-wetting part, which represents this behavior here, because this diagram is physically turned upside down. And so that's essentially what we're attempting to do. Likewise, perhaps more obviously, in the vadose zone, where we don't flip the diagram upside down, as we go up from the water table, again, this is atmospheric pressure by definition of the water table. As we go up in the continuous water phase in the vadose zone, the pressures are negative. So these water pressures are negative. A negative minus a negative is a positive. And the non-wetting fluid pressure is the pressure in the air. And the connected phase between the surface at atmospheric pressure and the groundwater table, also at atmospheric pressure, is atmospheric pressure, and that non-wetting fluid pressure is equal to zero, or essentially zero, because the unit weight is so small. And so again, it's this difference between these two pressures, the capillary pressure, in this case, again, positive, as we go up from zero capillary pressure to positive values here, up in this, gives us a magnitude of the saturation. So this is the capillary fringe. It's the sometimes referred to as the tension saturated zone. So it's saturated by the water that's in tension, but the capillary pressure is a positive value rather than the water. So this is the point which the medium is fully 100% water saturated, and as you get above that, it becomes less and less water saturation and more non-wetting saturation as that grows. That's it. So we did so well last time that we have a short class today, and I could go on if my voice wasn't hoarse and talk about what we'll talk about next time, but it's a fresh topic, and I guess it comes back to the figures that we're showing in the background. And the fresh topic is that the two figures on the right show the equilibrium behaviors once the material is present and is held by capillary forces. The behavior on the left-hand side merely shows the motion of the two fluids in the system. And so we talked about the different forms of saturation, and if we apply a pressure between the upstream and the downstream faces, then potentially we can move some of the fluid. The form of the saturation, as to whether it's predominantly water saturated and just a little bit with the non-wetting fluid, or the converse, mainly filled with the non-wetting fluid and only a small amount of the water, controls exactly when we suck fluid out of it, which one will move. If it's mainly water filled, then we suck fluid out, we'll get mainly water. And if it's the converse, we'll get mainly the non-wetting fluid. So what we need to now understand is that with these equilibrium saturations, if we apply a pressure between the upstream and the downstream faces, what will control the motion of the fluids that are present in there? Partly water, partly non-wetting fluid, air or NAPL. And the key to that understanding is really a bit like what we did with the describing what porosity was and what the saturations are, is that if we can think about the distribution of these two fluids and we can somehow centrifuge them so that we end up collecting the two fluids in different parts of the porous medium, then we can think about how the fluids would both simultaneously flow if we have a pressure difference between the upstream and downstream pressures. And we'll use Darcy's law, but we'll use it in a modified form to account for the cross-sectional areas within the porous medium, which are filled with either water, shown in red, and the non-wetting fluid, which is shown in green. And we'll save that for next time.